Welcome back. Today we are looking at circle dilation, as you can see by these dilated pupils in this eyeball. So let's dive right on in. Okay, we're going to look at circle dilation. The statement, all circles are similar, may seem intuitively obvious since all circles have the same shape even though they may be different sizes. However, we can learn a lot about the properties of circles by working on the proof of this statement. Remember that the definition of similarity requires us to find a sequence of dilations and rigid motion transformations that superimposes one figure onto the other. Zach is describing to Sion how he would prove that circle A is similar to circle B. Zach says, translate circle A until its center coincides with the center of circle B. Then enlarge circle A by dilation until the points on circle A coincide with the points on circle B. Or you could shrink circle B by dilation until the points on circle B coincide with the points on circle A. Okay, so that seems to make sense, right? Sion has some questions though. After one translation, what is the scale factor for the enlargement that carries circle A onto circle B? So he wants some more specific measurements here. What's the scale factor for the reduction that carries circle B onto circle A? So how would we answer Sion's question? So let's look back up here at this diagram. So we will have to think about this in terms of circles, but to help us make sense of that, let's think about it in terms of triangles, because we're more familiar with triangles, right? So let's say I have this triangle right here. And I have this triangle right here. Okay? We could say that these two are similar, right? Because their sides are proportional to one another. The question would be, okay, what is the scale factor when we are trying to move from one to the other? Well, if this side corresponds with this side, we know that we would just have to multiply by 2 to get there, right? The reason that we do that, though, is because we are actually looking at this relationship, okay? 2 to 1, or 2 over 1. The same way we could do the same thing with these two. 2 square root 2 over square root 2. And anything divided by itself cancels off, and we're left just with 2. So we take one piece of information about one of the circles, or the triangles, or circles, or whatever it may be, and relate it to another. Okay, so if we're looking at how we could make A coincide with B, we would just take this over this, okay? So to make A enlarge to coincide with B, we would multiply it by this value right here, okay? Notice as well, we're going to be multiplying by a number larger than 1, right? Because this is bigger than this, so we know that that's going to be a number larger than 1, which makes sense because we're dilating to make it larger. Okay. However, when we want to go the other direction, we need to multiply by a number that's smaller than 1. So we're going to take this, the number smaller, and divide it by this, the number that's larger. So to make B coincide with A, we would multiply by R1 over R2, which will be a number smaller than 1. Okay, so there we have that little answer to number 1. And now, based on Zach and Sion's discussion, we are probably convinced that circle A and circle B are similar. Another way we might convince ourselves is that the two circles are similar would be to find the center of dilation that maps the pre-image points from the circle A onto corresponding image points from circle B. So we need to find the same points, or corresponding points rather, from circles A and circles B. Okay, we're looking really for the center of dilation here, which we've done in the past before. So let's erase all this mumbo jumbo up here. All right. And now, in order to find the center of dilation, we already have this tangent line line RS that completes, or that continues along this bottom portion here. Now let's go ahead and find two other corresponding parts, like the centers, B and A. And we'll go ahead and draw a line between those two, like this. Now that means where these two lines, AB and RS, intersect, that is the center of dilation. So the center of dilation is right about there. Okay. Now, if we wanted to, we could also say, okay, these triangles are similar, right? Because this is parallel to this right here, not congruent, but parallel, right? And we know that tangents are right angles to radii. And so we've got lots of information that we could go off of there too, saying, all right, well, these two angles are congruent because they are corresponding angles of two parallel lines cut by a transversal. And then if two angles in a triangle are the same, then the third angle must also be the same. So we have triangle similarity as well, which means the radii are similar to one another. And if the radii are similar to one another, then the entire circle is similar. Alrighty, now we're going to move on to question number 3. Draw some chords, triangles, or other polygons inscribed in each circle that would be similar to each other. Explain how you know that these corresponding figures are similar. So let's talk about what inscribed means real quick. So inscribed just means that it's within a circle and each vertex lies on the circumference of the circle, okay? So let's go ahead and do that really quickly. I'm going to just give you one example. You're welcome to use it, or you could use another if you'd prefer, another polygon within here, okay? So I'm actually going to just use the two radii they've given me already, and I'm going to create a triangle, okay? Right there and there, okay? Now, what I need to do also is, I need to explain how I know that these corresponding figures are similar. And so what I need to do here actually is, in order to make them perfectly similar, I need to actually use what I know about them as, or what I know about these circles as, that they are similar. Okay, so I'm going to redraw this point AB. Okay. And that means that, okay, great, I know that R1 and R2 are similar to one another currently. But in order for me to make sure that this new point, I'm going to call it X, in order for that to be similar to my point Y on the next triangle, I need to coincide with my point on line RS. And that point needs to go through X as well. So boom, right there like that. Now I know this point up here, I'll call Y, that will create a similar triangle when I connect it now with S down here on the bottom. And, and B. Okay, so now that triangle, I've created a similar triangle where this side is similar to this side, okay? And then AX is similar to AY, or to BY, excuse me, and R1 is similar to R2. And I know that because they all go through this one point here, the point of dilation, okay? You could do that with any other triangle as well. And I would encourage you to try to do that as well on your own, to look at some different triangle options or even rectangles and things like that to make some more similar shapes. So go ahead and try that on your own if you'd like. Okay, now we need to create some proportionality statements that you know are true. So I'm going to let you go ahead and do that. So you could say something like AX over BY is equal to, and then you could make it something else, another proportionality statement. So go ahead and, with your own shapes or the shape that we use together, go ahead and write some proportionality statements. Okay, number 5. a proportionality statement we may not have considered. What convinces you that it's true? So they're saying that this proportionality statement is in fact true. Now, what would convince us of that? So right now it's just saying some words, right? Some vocabulary words. The circumference of circle A over the diameter of circle A is equal to the circumference of circle B over the diameter of circle B, okay? Now, it's kind of confusing to just look at it like this, so let's actually talk about what those things are, the circumference and the diameter, how we could represent them based off of our diagrams above, okay? So we know that a circumference, that is 2 pi times the radius. That's the formula for a circumference, okay? So in circle A, we have radius 1, okay? And I'm going to do 2 pi times radius 1, all right? And then my diameter, well, that's just 2 times the radius, all right? A diameter is just twice as long as the radius because it goes all the way. It's a chord from one side of a circle all the way to the other side of the circle through the center point, okay? So it's just twice as long as the radius. Now let's talk about circumference of circle B and the diameter of circle B. Well, since circle B's radius is called R2, I'm going to say 2 pi R2, and the diameter is just twice as long as the radius, so 2 times R2. All right, so now what we need to do is say, okay, how do we know that these are true, that this is equal to one another? Well, if I do some simplification, I know that 2 divided by 2 is just 1, so they cancel off. R1 divided by R1 is also just 1, they cancel off. Same thing on the right side, and I get pi equals pi. So I know that this statement is true, meaning this statement is true, and finally that statement is true. Okay, let's go ahead to number 6. Since the ratio of circumference to the diameter is the same scale factor for all circles, this ratio has been given the name pi. Some of you guys may have even memorized this when you were younger, or at least memorized some digits of it. I think I just have memorized out to 3.14159, and then from there it gets a little fuzzy. But we generally just use the first 3 digits, 3.14 of pi. So what we're going to look at is number 6, how much larger is the circumference of circle B than the circumference of circle A? And we just have variables right now, so we're going to actually just plug them in. We know the circumference of both of them, and then we're going to just simplify it, okay? So the circumference of circle B is 2 pi R2, and the circumference of circle A is 2 pi R1. So I'm just dividing one by the other in order to find the scale factor is really what I'm doing of the circumference specifically. Okay, so again, 2 divided by 2 is 1. Pi divided by pi, even though it's irrational and goes on forever, pi divided by pi is still 1. And so I get that the scale, how much larger the second circle's circumference is just R2 divided by R1. Okay, now let's look at number 7. Do you think the following proportion is true or false? Why? The area of circle B over the area of circle A is equal to the circumference of circle B over the circumference of circle A. Well, let's think about that. I actually want you to think about this for a minute on your own, and then we'll come back and talk about it in a minute. Okay, welcome back. So let's think about what are these things. Before, when they've asked us different questions, we've actually gone in and we've used the formula for the circumference or for the diameter. So let's do the same thing now with the area. So the area of circle B is going to be not 2 pi r anymore, but it's going to be pi r, and this is r2 squared. Okay, and then we have pi over r, or pi r1 squared for the area of circle A. Okay. Now when we're talking about the circumferences, let's talk about them as 2 pi r2 and 2 pi r1. Okay, so what they're asking is, are these things equal to each other? Well, when we simplify the left side, pi divided by pi is 1. Simplify the right side, 2 divided by 2 is 1. Pi divided by pi is 1. And we're left with r2 squared over r1 squared. And that's equal to r2 over R1, or is that equal to R2 over R1? That's what we're really looking at. And as you can see, actually, we can't just cancel these squares off, right? Because the opposite operation of squaring is square rooting, and that is not the same as just canceling off from a numerator to a denominator, okay? So we cannot just eliminate those. So that actually means that this statement is not true.